Thank you for that introduction. Thank you for the opportunity to present here today. Thank you all for listening. Today I'm going to be talking about the elements of history of breath analysis, which begins as far back in time as medical notes have existed. Breath odour was used by the ancient Egyptians. Eastern medicine taught smell as one of the 4 pillars of evaluation and agreed with what Hippocrates taught his students, such as rotting smell suggesting lung disease. The history and the present research into breath analysis is way too vast to compress into 10 minutes, so I'll concentrate on the work leading up to and utilising GC and GCxGC TOF-MS. That's gas chromatography and comprehensive gas chromatography hyphenated with time-of-flight mass spectrometry. The first GC-MS was a GC TOF-MS, built in 1956 in Michigan by McLafferty and Gulk. However, it wasn't until 1971 when Linus Pauling studied breath with a GC-MS that the true complex nature of breath came into view. He used a single quadrupole GC-MS because the data from the time of flight proved too vast and complex to work with. It wasn't until 1996 that a GC TOF-MS capable of recording all the data was built and production of the Pegasus began at the LECO factory in Michigan. Even then, the amount of data recorded proved too vast for computers to process in reasonable time until in 2000 when the gigabit processor was invented. In the same year, Professor Seeley of Oakland University, Michigan, analyzed chemical mixtures with flow-modulated GC-GC FID. Resolving complex data sets with computer power and complex matrices with chromatographic power took a huge leap forward in 2000. In 2002, LECO brought out the first GC-GC TOF-MS, the Pegasus 4D. I'm not going to go into the details of how GC-GC works, but for the uninitiated, it's a method of injecting all the effluent from GC column into a different GC column, and so separating in a second dimension, thus vastly increasing chromatographic resolution and separating coeluting peaks. Professor Seeley utilized flow modulation, whilst LECO's Pegasus 4D quadjet modulator used 2 liquid nitrogen cryotraps to refocus and trap analytes and 2 heaters to pass the analyte through the modulator and inject onto the second column. About the same time in Ann Arbor, Michigan, Mark Libidoni was building a different type of thermal modulator. Looking for a suitable complex test mixture, he chose breath, and the first GC-GC MS analysis of breath took place. Also in the same department was a Pegasus 3. They upgraded it to a Peg 4D on which his mentor Richard Sachs and Juan Sanchez analyzed the breath of smokers. Soon after, and before his work was published, Libidoni joined LECO separation science team in St. Joseph, Michigan. Unfortunately, Richard Sachs died before Libidoni's PhD paper was published. Research into disease is reliant upon research into instrumentation, and many of the early papers focus on this. Ralph Zimmerman's group at the Helmholtz Institute assessed multi-bed needle trap systems, and Michael Phillips worked on breath collection systems. With such complex field and so few researchers, papers were few in the 2000s. But Libidoni and Phillips did the rounds at conferences, drumming up interest with presentations and such. Dr. Phillips at Pitcom, Libidoni at the annual GC-GC conference ISCCE, and the ideal introduction to breath analysis for the uninitiated, Michael Phillips' TEDx talk. Around 2011, Dr. Stephen Fowler in Manchester, England used a Waters GC TOF-MS to investigate chronic obstructive pulmonary disease, and Silvia Rocha's lab in Portugal followed up their single quad analysis of asthma breath with a PEG 4D yielding 8 times the number of detected compounds to vastly improve their understanding. Asthma has become a focus for many labs utilizing time-of-flight mass spectrometry, including further work from Stephen Fowler with Roy Goodacre and Jeff LeConte's team in Liège, Belgium, although utilizing different ends of the TOF spectra, a GC TOF-MS in Manchester and a GC-GC high-resolution TOF-MS in Liège. Fowler and Goodacre's research with GC TOFs also extends to pneumonia, but at some point we must answer the question, Why do so many experts in breath analysis hyphenate GC-GC with time of flight? Thermal GC-GC produces very fine peaks, a tenth of a second wide, an ideal challenge for a fast TOF. So it was only natural that with full range spectra 200 times a second, the Pegasus would be utilized as a GC-GC detector. Thus, co-eluting peaks are separated by GC-GC, and fast TOF produces the complete fragmentation spectra for every peak. The latest instrument, the BT4D, records enough data points across a 0.1 second peak to reproduce accurate quantitation to boot. By 2013, Libidonia teamed up with Michael Phillips working on the influence of radiation chemotherapy on breath. Interestingly, the chemotherapy biomarkers should be very similar to those created by cosmic radiation, ideal for monitoring the health of astronauts on long voyages such as travel to Mars. They followed up their initial work on a single quad and compared single GC with GC-GC on a PEG-4D and resolved over 5 times more peaks, 5 times more opportunities for biomarker discovery. All the breath analysis speakers at September's virtual GC-GC symposium agreed that GC-GC analysis of multiple patients in a study typically identifies 2,000 analytes. One of those speakers, Heather Bean, works closely with another of the previous speakers here, Jane Hill, collaborating on pneumonia and tuberculosis research, and also has teamed up with another of this year's speakers, Pierre-Hugues Stefanuto, part of Jeff Racont's team in Liège, which leads me onto high-resolution mass spectrometry, as they have an HRT-4D, 200 spectra per second, comprehensive chromatography in excess of 50,000 resolution, sub 1 ppm mass accuracy, and a mass range of up to 1,500 AMU. It is a beast. Many argue that GC-GC provides by far enough data to work with, and we've seen a 5 to 8-fold increase in resolved peaks is typical. And I should add that the analytes identified in 1D will typically library match with 10 to 25% improvement when separated with GC-GC. However, the addition of accurate mass can further increase confidence in identifications. So if budget constrains your options, GC-GC TOF-MS is an excellent solution for many approaches, especially in biomarker discovery. But if you can afford a GC-GC high-res MS, then get the best of both worlds. We have, for the most part, talked only about thermal modulation. There is also flow modulation, which brings us right back to 2000 when Professor Seeley was performing GC-GC with his own bespoke flow modulator. LECO have since teamed up with them to design a new flow modulator. However, in breath analysis, no one that I am aware of has worked with flow modulation GC-GC hyphenated with TOF-MS. However, there is still a missing piece of the puzzle. In 1956, the GC TOF-MS was invented, but it wasn't until 1996 that the data was usable. 2000 when it was processable. GC-GC complicates that story once again, and now accurate mass. The one thing left is the software to process all this data. Not only is the data complex, but for medical research, for biomarker discovery, sample data needs to be combined with potentially hundreds of other samples. So if you're interested in how LECO can assist your workflow and statistical solutions, then get in contact and let us show you the power of GC-GC, time of flight, LECO patented deconvolution, and our latest LECO software. Now, there are many great researchers not mentioned here, from Ranjan Nanda's work in India on gender dimorphism and tuberculosis, to Audrey John's work on malaria, and my apologies to all those that I've missed. Now, what does the future hold? The soon-to-be released high-resolution multimode source will also give electron ionization, positive chemical ionization, and negative chemical ionization with perfect chromatographic alignment. As my daughter likes to say, epic.